Okay, so we have rotation about A by 120 degrees, rotation about A composed with itself for 240 degrees, rotation about B, the square of the rotation about B, you know, about C and that done twice, about D and that done twice. I have rotation by 180 degrees with an axis that pierces through AB and goes to the opposite edge. Okay, so I have R of AB. But what other ones would I have? What do you think?
Would you also have R of AC and R of AD?
Yeah, okay, R of AC. Okay, and R, so R of AC, I would have a vertex, or I would have an axis that goes through the middle of that edge to that opposite edge, namely DB. And then I would also have, you know, an axis of rotation going through AD, going to the opposite edge BC. So it'd be R of AD. Okay. And why don't I need to list anything else? Like R of BC, for instance.
Because that would be like the same as RAD.
Yeah, that's right, because that would be the exact same thing, right? Opposite edges are uniquely determined once I pick one of them. Okay. All right. So we have that. Okay. We've already labeled our vertices. Okay. So let's kind of start listing what these things are. Okay. Look, I'm not going to make anybody list the identity. I can do that easily. There it is. Okay.
Dr. Hammett.
A.
Oh, okay, never mind. It's recording. Sorry, my question was answered.
Okay, row A. What do you have? What do you have, Paul? How's that going to look?
So row A, let's see. Okay, so let me see. So it's rotating I'm assuming it's rotating the direction that it is in the picture, and therefore A stays the same.
Yeah.
B goes to D, D goes to C, and C goes.
Yeah. Okay. And then what about, just for good measure, Paul, what about row A squared? I'll help you out here. A stays where it is.
Okay. So then C goes to, I'm sorry, I'll start with B. So B would end up at C, and then C would end up at D, and D would end up at B.
Yeah, exactly right. Yeah. Okay. And by the way, there's going to be a lot of other things, but do you see that they're all going to be a 1 cycle followed by a 3 cycle? Yes? You guys see that? There's going to be a bunch of 1 cycles followed by 3 cycles. Let me use green here. This guy right here is going to contribute an X1. That's it's 4 1 cycles. This guy right here, of course, is going to be X1, X3, same thing with this one, right? But the thing is, not much is going to change all the way through all of the rotations. Do you know what I'm saying? Okay, through all of these rotations, it's going to be exactly the same. And row D squared is the last one of these. Mary, are you still in here?
Yeah, I'm here.
So what does row D squared do? How would I write that?
So it would just be D as a cycle, and then would C go to B and then B go to A?
Yeah. C would go to B, B would go to A, and where would A go?
A would go back to C.
Yeah, okay. A, C, B. Of course, we would kind of have to know the rotation exactly. You understand what I'm saying? I didn't draw the axis exactly, but does it really matter? Mary, does it really matter like which direction I'm rotating technically?
I don't think so.
No, okay, right. So this again would be an x1, x3. Okay. How many of these x1, x3s were there total? Anyone?
I want to say 8.
Yeah. There are 8. Okay. And then what about R of AB? Somebody help me out here. R of AB. R of AB. Cassie, you in here?
Yes.
So what about R of AB?
Okay. A would go to B and B would go to A.
Yep.
And D would go to C and C would go to D.
Okay. And finish us off here, Cassie. So R of AC, what's going to happen with that?
Hold on. A would go to C and C would go to A. D would go to B and B would go to D.
Okay. And then finally, AD.
Yeah, A would go to D, D would go to A, and C would go to B, and B would go to C.
And each one of those, what are each one of those going to contribute in the form of a cycle index polynomial summand?
That's just x sub 2 squared.
Yeah. Right. All of these, right? And I'm just going to write 3x sub 2 squared because there are 3 of them. Yeah?
Yep.
Is everybody with me on that? All right. Well, that is why, let me just kind of go over here. Okay. That is why, my friends, this right here ends up being the cycle index polynomial for the tetrahedron. Do you see this right here at the bottom? Okay, this thing right here. Okay. The 1/12 is coming from 1 over the size of the group, x1 to the 4th. That is the identity permutation. 8, x1, x3, that's coming from the 8 rotations about a vertex. And then the axis midpoint opposite edges, that contributes the 3x sub 2 squared. Does that make sense? Hopefully. Hopefully that makes some good sense. Okay. All right. Questions? Any questions on that? Anything at all? Okay, so eventually I'm going to do some much more interesting examples. Okay, so let's just think together for a minute, okay? What if I were to color the vertices of a cube? What sorts of symmetries would you have for the cube? Can you guys think of symmetries of the cube? You guys know what a cube looks like, right? It looks like this. Yeah. There are 8 things to rotate around, right? What sorts of symmetries could you imagine would exist for a cube? Let's just talk about it, right? Just kind of structurally, how would we think of certain symmetries of the cube?
I feel like this is just off the top of my head. I haven't thought about it a huge amount, but I think you're gonna have basically a symmetry for every opposite pair of vertices and a one for every opposite pair of edges, and then one for every opposite pair of faces.
Yeah, so let's just kind of quickly start to sketch what our thinking is on this. If I had A, B, C, D like this, okay, and then E, F, G, H like that, okay, then what are you thinking about here? So what are you thinking about here, Paul?
Okay, well, so for rotations, for example, you could think of it as like well, for example, you could run a vertical line through the top face and the bottom face, and
Oh, okay.
just have those basic, and then that would give you, I guess, a 90 degree, and then a 180, and then a 270, and of course you already have the 0.
Okay, so you could do things. So what Paul is saying is, hey, why don't we just put like an edge right through the middle of two opposite faces? Yes, like that, and then maybe rotate around that.
Mhm.
So I don't know what to call that. Maybe like row A, B, C, D for the face corresponding to A, B, C, D, and then we just automatically go to the opposite face, correct?
Sure.
Okay. And so how many degrees do you think we should assign to the original one? Maybe.
90.
Yeah, let's just do 90 degrees. And then I would need to not, I would not just have this one, but what else?
You'd have that squared and then that cubed.
Exactly right. Okay. And how many of those face facial rotations would we have?
So you have 4 for this pair, and then let's see.
Well, not really, because the identity is gonna kind of, you don't really have 4, you have 3, right? I mean, the identity is kind of like its own animal. Does that make sense?
Oh yeah, I see what you're saying. You're
Yeah,
right.
yeah.
Because if we did it as 4, then it would be like we'd have an identity for each of the pairs of faces.
Mm-hmm.
Okay, I see what you're saying.
Yeah. So what else?
So would it be 10 if you include the identity, because you've got like 3 additional ones for each of the opposing faces?
Yeah. So I don't know. Let's do C, D, E, H or something like that, right? Row C, D, E, A. Oops, H. Okay. That's the face corresponding to C, D, E, H. And then I would have to square that thing and cube that thing. Okay, and then finally, let's see, what other one would I need? Maybe A, D, E, F or something. Row A, D, E, F squared. Oops, I put squared. What did I mean right here? Sorry.
That should be cubed for the last one.
Yeah. And then row A, D, E, F cubed. Okay. Interesting. And what about the cycle structure? Let's just think about, so these are all the facial rotations. What would the cycle structure be? So somebody could speak into this. First of all, we know the cycle structure for the identity is trivially just going to be x1, right? It's a bunch of 1 cycles, and it's going to be x1 to the 8th. Does that make sense? Yeah? Okay. So what about this guy right here? What would the cycle structure summand for the cycle index look like for the facial rotation A, B, C, D?
Would that just be x sub 4 squared?
Yeah. Okay. And what about the cube, Elise?
That would also be x sub 4 squared.
Okay. And what would the square contribute?
X sub 2 to the 4th.
Yeah. Amazing. And by the way, each one of these, right? I mean, you guys see the right, you're going to have the same thing true for all of the things that are just simply 90-degree rotations, right? And the same thing is going to be true for these guys that are all 180-degree rotations. And the same thing is going to be true for these 270-degree rotations. Okay? Yeah. What about other symmetries? So we have 10 symmetries so far, and all we've thought about are the faces.
You could draw an axis through each pair of opposite edges or vertices.
Ooh. Yes. Okay. So let's see here. So you can do opposite edges or opposite vertices. Nice. Okay. So how would you, okay, let me, oh man, I'm running out of room over here, but I mean, I think you guys get the picture here. So opposite edges. So like you're thinking something like, you know, row AB, okay? So in row AB is going to be, so this is going to be 180-degree rotation through an axis piercing which edges? What are you thinking of, Cassie? Edges.
I can't see. A, B, and E, H.
Yeah, AB and EH. Exactly right. Yeah, those opposite things. Exactly right. Okay. So I would have that. Okay. And of course, if I square that, I'm just back to the beginning. Do you understand what I'm saying here? Like you don't have row AB and row AB squared. Row AB flips it. Row AB squared puts it right back to the beginning. Know what I mean? It's going to be like that. Okay. And okay, what else would we have? Row what?
CD.
Yeah, row CD. Okay. Row CD, that would go to the opposite edge, FG, and we would do a 180-degree rotation through that axis, around that axis, yes. And what's another one that we would have?
You'd have row AD and row BC.
Yeah, row BC. Is that all? Wait a minute, you had row BC.
Row AD.
What? Okay, so hang on, what's that?
Sorry. I'm following the four edges on the top of the box.
Oh, I see. Row
They're
AD.
not orderly.
Got it. Got it. Okay.
Yeah.
And Cassie, you are the master of edge, you know, 180-degree edge rotation. So what do each one of those contribute?
Do you mean like the X sub?
Yeah.
Would it just be X sub 2 to the 4th? No, that's not what it is.
Is it? Well, hang on. So it looks like that entire, I mean, it would have to be a bunch of 2 cycles. Does anything at all get fixed? Think about it. Do any vertices stay in the same place when you
Yes.
put them around one of those axes?
I think so.
You think something gets fixed?
I don't think so anymore.
Okay, like that, and I'm going through like this and this. Yeah?
Yeah.
If I rotate around that thing, I don't think anything stays
Oh.
in the same place. So it's going to be a bunch of 2 cycles, right?
Yeah.
How many 2 cycles are there going to be?
There'll be 4.
Yeah. Okay. So we have all those. And what about, okay, so what's the last, I mean, so you know, I don't want to necessarily put Cassie continuously on the spot here, but she already mentioned another rotation. What was it?
It was going from corner to corner, like vertex to opposite vertex.
Yeah, vertex to opposite vertex. And how many of those are there?
Also 4.
Also 4 because,
Axes.
right, because there's a bunch of paired vertices, yes?
Mhm.
So what's weird? Oh, wait a minute. So did we miss some locations
We
around?
have to do CH and DE.
Yeah.
Oh, yep.
Okay, so tell me which ones again, Katie?
So on the right side, you can go from CH and
Yeah,
then from
so
DE.
she's thinking about CH over here. You know what I'm saying? Yeah. The ones that are kind of going down from the top face of the bottom. So it'll be row, what is it?
CH and then DE.
Row DE. Okay. And all of those are still going to contribute x2 to the fourth. You know what I'm saying? Each one of those is going to contribute x2 to the fourth. Okay. But now, but now Cassie is going to say there's a bunch of opposite vertex rotations. Yeah.
Right.
So like you're thinking of things like row A, and you know what row A is, right? Row A just means it goes through this and it goes over to this opposite thing right here, and as incompetent as my picture is, that's what's going on, right?
Mm-hmm.
Kind of rotating in that direction. So there's row A, but what else would there be?
Row B, row C,
Yeah.
row D. I think that's
So
it.
row B, row C, row D. That's good.
Yeah.
Also, what else would you have to do? So first of all, how much rotation is happening? Think about it. If I'm rotating on one of those vertex axes,
Mm-hmm.
how much rotation is actually happening?
90?
Not 90,
180. 180.
not 180.
270.
Huh?
270.
No,
Wait,
not too
so we're rotating around 0. I don't know.
So if you rotate around A, right here, yeah?
Uh-huh.
So think about it. How many times am I going to have to rotate to get back to the beginning?
To this identity.
So like, isn't B going to go to D? Okay, hang on. So let me pick a color here, like black maybe. Okay, or isn't D going to go to B? Right. So D is going to go to B, and where's B going to go?
To G.
I don't think so, because it's like you see those three. It's like a three-legged spider that's kind of spinning around. Does that make sense? So isn't B going to end up down here?
Yeah, I see.
Yeah. And then this is going to go like this. Do you see that little cycle that's going to be formed by those three vertices? Yes. B, F, D, B, F, D. Those three edges right there are going to be like rotating into one another. Does that make sense?
I think so.
So what does that mean? B is going to have to be rotated a total of 3 times to get back to the beginning. So what's that? What is the degree of rotation that we must have started with?
$120.
Yeah. But that tells you that there's more than one rotation happening there. It's not just row A, it's also row A squared. And then row A cubed gets you back to the identity. Yeah?
Mm-hmm.
Row B squared, row C squared, and row D squared. Yes. Okay. So that being said, oh, that's interesting. So what about these guys right here? What about all of the 120-degree rotation guys? What do those contribute to the cycle index polynomial?
You're going to have A by itself and H by itself, and then you're going to have 2 X of 3s.
So you're going to have two 3 cycles. Does that make sense? So you're going to B, D, and B and F in a little 3 cycle, and you're going to have C and G and E in a little 3 cycle, right? That little 3-legged spider is going to be spinning around that thing. Okay. So what do we have? X1 squared, X3 what? How many 3 cycles are there?
There's 2.
2 of them. And what about these guys? What about these guys right here?
I think they'll be the same.
Yeah, why? Yeah, that is true.
They'll just have different like groups of 3 that you'll be switching.
Yeah, yeah, right. So you would go backwards by 120 degrees, yes?
But the same 2 vertices would be
So
x
you would
of
also get it from that thing. So what's the cycle index polynomial? Let's finish this off here. Actually, I'm going to use a different color. What's the cycle index polynomial going to be? Well, first of all, we need to count the total number of permutations that we have here. What is it? Man, seems like it's a massive number of permutations. I had 10 over here. Yeah. What did I have? 1, 2, 3, 4, 5, 6, and then 8 more. So all told, I had how many symmetries? Wasn't it 24? Yeah. Because it's 10 plus 6 plus 8, 24. And of course, I have x1 to the 8th. Okay. How many x4 squareds did I have? Can someone help me here? How many x4 squareds were there?
There's 6.
Were there 6 x4 squareds?
Yeah, the 90-degree rotations of
Oh,
the
yes.
70 of faces.
Yeah. So there were 6 of those. Okay, and how many x2 to the 4ths? How many x2 to the 4ths did we have?
9.
9. Excellent. And how many, what else do I have? So I have 9 x2 to the 4ths. I think the only thing I haven't accounted for are the vertex rotations, right? And all of those were x1 squared and then 2, 3 cycles. So I have a total of 8 of those. Is that right?
Yeah, just
What
8.
should I count to make sure I've accounted for everything? What should be true about the coefficients if I add them all together? What should I get?
Should get 24.
Do I? 15 and 9 is 24. Yep. There is the cycle index polynomial. Somebody could hand me any number of colors and I would immediately be able to tell the number of distinctive colorings of the cube. Now, I mean, I have no business counting something like that complicated. You know what I'm saying? But what's going to happen in the next section is we're going to be able to say even more. We're going to be able to actually deliver a pattern inventory. We're going to be able to say, well, actually, there are this many distinctive colorings of the vertices of the cube that have 3 reds, 2 blues, and 1 white. We're going to literally be able to count the number of those things, and that will be a nice. That's called Polya's enumeration formula. Actually counting not just the total number of colorings, but giving an actual inventory for these things. So that's good stuff for sure. I mean, do you guys understand? We have no business counting such a beast. No business. And we just did it, right? So that's an amazing thing to behold for sure. And we could have been coloring edges, yeah? We would have just had to label edges instead and think about edges going into each other rather than vertices. We could have colored faces, and we would just have to think about faces flowing into each other and how the permutations affect those as they move around, okay? So that's a thing of beauty right there. We'll look at a couple of other Platonic solids. Specifically, we'll look at the dodecahedron, and the icosahedron. The dodecahedron is the one built from pentagons. The icosahedron is built exclusively from triangles. But that's interesting. And in your homework, you'll have some specific examples you'll look at, and you'll have to come up with groups. And incidentally, I didn't have to look at all of the symmetries of the cube. I could have just restricted myself, for instance, to facial rotations. And I still would be able to say, okay, how many non-equivalent things do I have through facial rotations? And I would still be able to do it. That's a fairly amazing thing. And what's this little, there's some chat things over here. I wish I had a Rubik's Cube right now. As he said, yes, Paul, modern problems require modern solutions. Yes. Okay. I actually do have a tetrahedron somewhere. I have a tetracube. Oh, well, that doesn't even make any sense. What is it even called? Like, you know, one of those tetra puzzle. Okay. I have one of those, but I don't have a Rubik's Cube on me, unfortunately. Okay. Any questions about any of this?
Could you explain, is there any chance you could explain really quick, I kind of missed it, why like whenever we rotate it through opposite vertices, there's like two separate ones apart from the identity instead of just one? Because visually I'm having trouble like figuring out like why that would be.
Two separate ones? What do you mean two separate ones?
Well, didn't we say that, like, I don't know, maybe I just misread something. Let me see. Didn't we say that, like, when you're rotating it through the vertices, it's 120 degrees and then 240 degrees rather than just 180 and then 360?
Well, because you have this little claw. Hang on, I'm going to have to move this thing out of the way. Can you see the picture over here? Actually, can I? Yeah, I need to make some room somewhere. Here, this is what I'll do. This is what I'll do. Okay, here we go.
Because literally everything else made sense, but I'm just having a little trouble with that one.
Okay, so let's look at this. So the cube looks like this, right?
Mm-hmm.
Oh man, that back end looks horrible, but you know what I mean. Okay, let's call this I don't know, I'm gonna relabel things. I'll call this B, I'll call this C, and I'll call this D. And I won't really pay attention to any of the other things, but one of the things we had, so what did we have? We had this axis coming in here.
Mm-hmm.
And we were kind of rotating like this, okay? So where is this edge right here, Paul? Where's that edge gonna go when I rotate?
It's gonna go to where AC is now?
Yes. That thing is gonna go right there.
Oh, okay.
Okay?
Okay, that.
And where is this edge gonna go?
And then its next stop, if you would be to where AB is?
Yeah. And then finally, it would go back down to here. Does that make sense?
Okay, that picture that's just focused on that part, yeah, that makes a lot more sense.
Okay, so that's why I was saying the thing about the three-legged spider. Know what I'm saying?
Oh, that's what that was all about. Okay.
So it's a three-legged spider. I'm just going right like that, right? I'm spinning that thing on that little axis.
That makes sense. Okay.
Yeah.
Thank you for
my son's standing here saying, a three-legged spider, Dad. That doesn't make any sense. But I say it does make sense. I just drew it, therefore it exists. Okay? Mathematically, at least. All right. Okay. Well, that's all I have. Thanks for coming in. The guy actually came in a while ago and snapped a bunch of pictures and then left in like 5 minutes. But hey, It was cool, kind of talking about things, sorting stuff out. I'll post, I think I'm probably only gonna post the more complicated stuff. The beginning stuff's kind of easy. I'll post like the cube development. That from that part onward, I'll post that just so that the thing isn't like massive or something, okay? Otherwise it takes forever to process in YouTube, okay? Homework due Monday. Didn't I say that? And I think I'm gonna combine the last two sections of the homework and have it be one on section 9.3 and 9.4. And chapter 10 is just gonna have to wait for the capstone, if indeed that's something you wanna take, okay? All right. Hey, thanks for coming.
Thanks, Dr. Hammock.
All right, see you
See
later.
ya. Yeah. Bye, guys.
Bye.